Now we're going to take the Newton method that we've done for scalar equations and extend it to work for systems of equations. And it's going to use the very same idea, which is that we have a current iteration, we have a current guess to the root, and in the vicinity of that root we build a linear model for our function. It's an approximation that's valid near the guess. Then we solve that linear model and call that solution the next iteration, or the next guess. So here's our capital F that maps n variables to n variables, or n variables to n values. So if we have a function f of x, we linearize. So L is the linearization. Of f at xk, the kth iteration. And so that consists of the value at xk plus the Jacobian at xk times x minus xk. So now the L will be a substitute for capital F. We set L equal to 0 and we call that root the next iterate. Okay, so this is the next value. And if you do the algebra from the previous line, setting that equal to 0, rearrange, remembering that J is a matrix now, so you can't just divide, you have to use a matrix inverse. We get this formula here, which is Newton's iteration applied to a system of equations. So the output of this iteration is a sequence of vectors. You give it x0, and then you plug in, for k equals 0, you plug into this formula. Out comes x1, a new vector, right, which is the guess at the root. And then you plug it in for k equals 1, and out comes x2, and so on. So you have to be given the starting value, just like in the scalar case, and then it produces the rest of the values from this formula. Now, the formula itself has a matrix inverse in it, which is fine as far as formulas go. But in numerical computing, in numerical linear algebra, we never find the inverse of a matrix. Whenever you see the inverse of a matrix, that means that there's a linear system that's being solved. And we use LU factorization for that. So in more detail, these would be the steps, okay? So these would be the steps in going from xk to xk plus 1. Okay, so first step we set r equal to f of xk. That's the current value of the system. Remember, that's the thing that we're trying to make 0. Then we let A be the matrix, which is the Jacobian evaluated at this point. Remember, the Jacobian matrix depends on the variables. So we evaluate it, and now we get a constant matrix A. Then we solve the linear system, A delta equals minus R. So this is a linear system solution in step 3. So the default choice would be to use PLU, for example, to solve that. And then with that delta, we finally know how to compute xk plus 1. Xk plus 1 is xk plus delta. So delta represents the difference, or sometimes it's called the Newton step. So we would repeat these steps over and over again, okay, going from xk to xk plus 1 as k increases. And we repeat it until we were done. How would we know we were done? Well, we're trying to make f equal to 0. So if the norm of r becomes small, then we can stop. Or, if the steps become very close together, if the sequence seems to have converged, we'll stop. So in other words, if the norm of the step size is going to 0, we'll stop. So if small, stop because we're done. On the other hand, we know that Newton's method doesn't always converge from every starting guess. So if the sequence is diverging, we want to give up. So if k gets too large, and you have to decide in advance what too large is, then we stop because we failed. So these 4 steps would appear inside a while loop, for example. Okay, let's see how it goes just doing it on paper, or virtual paper in this case. So here's a 2x2 system, 2 variables, 2 equations, and a starting guess. So it's helpful to evaluate the Jacobian analytically so that we have it for later. All right, so J, okay, we have df1, dx1, df1, dx2, right? So the row tells you which equation or which output, and the column tells you which input variable. So df1 dx1 is 3 minus 2x2. df1 dx2 is just minus 2x1. df2 dx1 is 2x2. And df2 dx2 is 2x1 minus 1. Okay, so now we plug in, we will evaluate f first of all. So step 1, r is equal to f of x0. So you plug in 1 for both variables, and we get 3 minus 2 is 1, and 2 minus 1 is 1. Step 2, evaluate the Jacobian. So you plug in 1 for both variables, we get 1, negative 2, 2, 1. Step 3, we solve A delta equals negative r. Okay. So we can do the LU factorization by hand. So we add 2 times the first row to the second row. And we get, we'll just do Gaussian elimination rather than LU factorization here. They're equivalent. So we leave the first row alone. Add minus 2 times the first row, add that to the second row. So this becomes 5, and negative 1 plus 2. Right now it's triangular, so that tells us delta 2 is 1/5. Delta 1 is negative 1 plus 2 delta 2, all divided by 1. So we get negative 3/5. Okay, and then finally step 4, x1 is x0 plus delta whoops, that should be 6/5. And there we are. Okay. What's the convergence of this method now, Newton's method? Well, it's not as easy to derive as it was in the scalar case, but it's similar. And we do conclude that it's quadratically convergent in the sense of taking norms of the error vectors. So as usual, we define ek to be the difference between xk and a root. So it's the error sequence. And if you do that, and if it does converge, then it converges at a quadratic rate. The ratio of the norm of ek plus 1 to the norm of ek squared approaches a constant. It doesn't matter what vector norm you pick, they'll all give you that same result, although the constant will be different for different norms. Okay, so that's pretty much the same as it was before. But one thing that's changed a lot is the computational cost picture. So now f is a vector, right? So there are n variables and n values. Now, if each value depends only on a few of the variables, right, then it probably takes about n flops to compute one value of f of x. Okay, so each time we plug an x into f, we do, let's say, a constant number of work for each component, then the output would take on the order of some constant times n flops. Now, if each output depends on all the variables, okay, then each output takes order n to compute, and the total cost would be order n squared. So it just depends on the problem. But now when it comes to computing the Jacobian, before we just computed the derivative of a scalar function, and we said that's about the same as the original. But now when we do a Jacobian matrix, there are n squared entries in that matrix. And so it's probably going to take, in the general case, at least n squared flops, okay, just to fill them all in. And maybe more. Again, might be more in some problems. So in the general case, it might be much more expensive to do J than f itself. And then it goes even beyond that because we have to solve a linear system with that Jacobian matrix. And we know that unless the matrix has some special properties, it's going to take some constant times n cubed to solve that problem. So this n cubed now becomes the limiting step, the most expensive step. It's order n cubed. This is for each iteration of Newton. I mean, one way of looking at this is that to solve the nonlinear problem, we're solving a sequence of linear problems of the same size. Okay, and each one of those is the kind of thing that we were doing at the very beginning of the course. And that's not to say nothing of how hard it is to take the Jacobian in the first place, do all those derivatives, and code them up accurately. It's a much bigger effort than it was in the scalar problem. And so because of these factors, it doesn't necessarily help with the order n cubed problem, but it does help with the differentiation problem to have an alternative where we don't have to compute the Jacobian manually.